All right, hello everybody. Welcome to part D of question D of part 3. I don't know how I'm numbering these, where we are asked to find the expected welfare of the optimal solution by solving for the expectation of the negative loss of the central bank. Okay, so this is a big computation, maybe the biggest computation we've done in class so far. And to be honest, I had to do this video a couple times because I tried to just charge straight in, and that's absolutely not the way to do it. We need to take it out in bites. And this is where algebra gets messy. So yeah, let's see if we can keep it clean and make it make sense. So to begin from the beginning, we're going to be looking at the utility of the society, which we discussed previously with the utility of the central bank plus the utility of the households. And we argue that the utility of the households is 0. This is 0 in expectation because of what the household's utility function looks like. You have, it's negative parabola. You have this maximum point here. This axis is expected utility. This axis is the utility of the household. I'm sorry, expected inflation. It goes down, and the maximum point is at pi, and the optimum value is 0. So we are at the optimum. We know that the optimum value is 0, at least in expectation. And you can confirm that if you really desire. You can work out the algebra, but it works out. So all we need to worry about is the utility of the central bank. The utility of the central bank is equal to the minus of the loss function. So the social utility is going to be equal to the minus loss function, and we call it the loss function is, it was plus 1/2, so now we're minus 1/2, y minus k squared. And then, sorry, this was 1/2, this was lambda over 2. And then minus 1/2 pi squared. And so our goal is going to be to plug in for y. And we remember that y is equal to yn plus a surprise inflation, pi minus expected pi, plus a shock. And we need to remember that the shock is normally distributed, mean 0, sigma squared variance, epsilon. You parameterize it. I like parameterizing with the standard error, as you like. Okay, so before we charge in, so this was the mistake I made. Right away I was like, okay, well, we're going to plug in pi star. So this is going to go here, okay, and then this is going to go here. And then, okay, well, there's a pi here, so we'll plug this in here, yeah, and then there's a epsilon pi here, so we'll plug this in here, and then we'll plug this in here, and then this turns into a huge mess. Okay, so we need to take it in chunks. We need to definitely take it in chunks. So let's look at some preliminary calculations. Let's not even touch the utility yet, and let's just look at some preliminaries. Okay, preliminaries. The first thing I would like to know is, what is pi star? After we substitute this into here and see if we can simplify it down a bit. So pi star is equal to a lambda over 1 plus a squared lambda. And then we get a squared lambda, k minus yn. So all I've done is I've substituted this into here. K minus yn plus, and I'm going to just draw brackets because I'm allowed to do that, but it'll make my point clear, k minus yn plus epsilon. So we see we have a k minus yn here, we have a k minus yn here, so we can factor out a k minus yn from these two terms. So we can write this as a lambda over 1 plus a squared lambda, and then we'll get 1 plus a squared lambda k minus yn plus epsilon. And that will give us, so that now we'll just multiply this in, this and this will cancel. So we'll get a lambda k minus yn plus a lambda over 1 plus a squared lambda epsilon. This should be a minus. I made a mistake. Here and here. How do I get rid of this now? X. Sorry. this should be a minus sign, this should be a minus sign, this should be a minus sign, right? Because it comes from this equation, which is wrong. That should be a minus sign. I apologize for that. Minus epsilon, minus epsilon, minus epsilon, minus epsilon. Okay, so that's our pi star, which is nice, which is very nice. And we can go one step further. We can ask what is, so preliminary 2, we can ask what is the expected value of pi star squared, yeah? Because that's the number we're really interested in, because that appears here, okay? So what we need to do is square this and take expected value. So the expected value of the quantity a lambda k minus yn minus a lambda 1 plus a squared lambda epsilon all squared. Let's make some more space. I think I learned how to do that. I do like this, and I do like this. Haha. I'm learning. Okay, so we need to distribute this. So let's just do it. There are, you can do some reasoning shortcuts with the expected value, but let's just do everything out to be very, very clear. We get a squared lambda squared k minus yn squared. So that's just this times itself. I'm just foiling, right? Now there's going to be this times this, minus this times this minus this times this. They're both negative, so it's going to be minus 2. And it's going to be a squared lambda squared over 1 plus a squared lambda k minus yn epsilon. So I just multiplied this times this. That's a y. And then we add this times itself. So a squared lambda squared over 1 plus a squared lambda epsilon squared. Now we take expected value, and we need to remember number 1, expected value distributes over addition. So we can go, we'll have 3 terms, this expected value, this expected value, this expected value. And 2, the expected value of epsilon is 0. And I guess that was 3. 2 is we can factor out non-random multiples from the expected value. What I mean is that if x is random and a is deterministic, then the expected value of ax equals a times the expected value of x. Okay, that's what I mean by that. You can factor out deterministic multiples from an expected value. So this is deterministic. We're just going to get itself back. A squared lambda squared k minus yn squared. This goes to 0 because we're going to factor out all this is deterministic, and then we're going to be left with the expected value of epsilon. And as we wrote up above, the expected value of epsilon is the mean because it's normally distributed. If we scroll back up, we have that here. The expected value of epsilon is distributed normally, so the expected value is the mean, and the mean is 0, so it's 0. Okay, so that equals 0. So this whole term will go to 0. Expected epsilon equals 0, so this all goes to 0. And then this one's a little trickier. We need to realize that, so what you need to remember is that the expected value of a normally distributed variable with mean 0 is equal to the variance of that variable. Why is this true? If you write down the definition of the variance of x is equal to the expected value of x minus the expected value of x squared. Okay, the squared difference between x and the expected value of x. So you're centering the random draw and then squaring the distance from the mean. So it's like the spread around the mean, right? And it's the unsigned distance from the mean. So again, it's sort of like an absolute value. This, if expected value is 0, so if we think about the variance of epsilon, which we know the expected value is 0, we'll get the expected value of epsilon minus 0 squared, which equals the expected value of epsilon squared, okay? And that's the variance of epsilon. And for a normally distributed random variable, that is the squared standard error, just the definition. So that's how we get sigma squared here. So we're going to end up with this plus a squared lambda squared over 1. I wrote a minus here, that should be a plus, right? Yeah, 1 plus a squared lambda sigma squared epsilon. And then we have an a squared lambda squared here, we have an a squared lambda squared here. I'm just thinking, is it profitable to distribute it out? Maybe. We could write this as a squared lambda squared times sigma squared epsilon over 1 plus a squared lambda plus k minus yn squared. Okay, so this is the expected value of pi star squared. So this is an important preliminary. We can use this and plug it into our answer. Now there's one other important preliminary I want to look at, which is, so I mean, really, we kind of did this whole first half. So now we know the solution to this part, right? We know that this part is going to be equal to the thing we wrote down there. I'm not going to clutter it up by writing it again. Now we want to look carefully at y minus k. So what is y minus k? Let's substitute everything in for y first. Let's just quickly write that down. We'll get y equals yn plus a. Pi, we know what is pi if you substitute everything down. We wrote that down somewhere, didn't we? Yes, we said if you substitute pi star all the way down, you get this equation. So it's going to be a lambda k minus yn minus a lambda 1 plus lambda square a squared lambda, well, I cannot speak, I'm sorry, epsilon. Now minus expected pi star, which is a lambda k minus yn, which already you see this is quite nice. K minus yn. And then, so we're still looking at y, so if y, a, all of this is the term lambda minus pi lambda, this is all that, and then we need to add epsilon. Yep. So you can see this cancels with this, so we're left with y equals yn plus epsilon minus a squared lambda over 1 plus a squared lambda epsilon. And we have an epsilon and an epsilon, so we can factor. So we'll get y equals yn 1 minus a squared lambda over 1 plus a squared lambda epsilon. And this is plus. And you see we can do the rewrite 1 thing. So 1, we'll write it as 1 plus a squared lambda over 1 plus a squared lambda, and we're going to get, as our final answer, y is equal to yn plus, the a squared lambdas will cancel, right? So we'll just have 1 on top. So it'll be epsilon over 1 plus a squared lambda. Yep. Okay, so this is our y. So we just need to subtract k and then square it and find the value of that square. So let's go back down to our preliminary section. So our preliminary section 2 is we want to know what is the expected value of y minus k. I guess we're in preliminary 4. I don't know. This whole naming schema has collapsed. I'll call it 3. we want to know what is the expected value of y minus k squared. And we know the expected value of y. We scroll back up a little bit. The expected value of y is, so we're looking for the expected value of yn minus k plus epsilon over 1 plus a squared lambda squared. Okay. Now I'm going to do this square, and when I do it, I'm going to draw some new parentheses. I'm going to, in my mind or on my paper as I like, I'm going to add a parentheses here. And I'm going to do that because I see this term, k minus yn here, and so I think maybe it's nice to keep all the k minus yn together, and something magical will happen at the end. Or at least maybe it'll be convenient. So I'm going to do the distribution. I'll get the expected value of the first term by itself, or times itself, is yn minus k squared, plus the cross terms, 2 times, how to write this? Let's write it as 1 over 1 plus a squared lambda yn minus k epsilon. And then the last term times itself will be 1 over 1 plus a squared lambda squared epsilon squared. Now I can take the expected value and all of the rules that we keep talking about apply. So this is deterministic. The first part is deterministic. It just carries along yn minus k squared. The second part has an epsilon. I factor out the deterministics from the expected value. I'm left with expected value of e is 0, so it just goes to 0. So this is 0. And then here, factor out the deterministics, and remember the variance, the expected value of epsilon squared is equal to the variance of epsilon. So we're going to get plus sigma squared epsilon over 1 plus a squared lambda squared. Okay, so now we have all of the preliminaries that we need to tackle the problem. So now we return to our initial question, which was what is the expected value of minus lambda over 2 y minus k squared minus 1/2 pi squared at pi equals pi star expected pi equals expected pi star. Okay, I've been lazy with the conditioning information. You should write a bar here and you should put this stuff here. I'm sorry about the lack of formal precision in my writing. Okay, we're almost there. We're almost there. So first thing, we can distribute the expected value. So this is equivalent to, we know that lambda over 2 is non-random. So let's put it outside. Lambda over 2, expected value of y minus k squared, minus 1/2 is deterministic, expected value of pi squared. And we know that y minus k squared is random because there's epsilons hiding inside the y, and we know that pi squared is random because there's epsilons hiding inside the pi. Okay, but we already computed what is this and what is this, right? So let's just use what we worked so hard on. So we bring in minus 1/2 times, we computed this, yn minus k squared plus sigma epsilon squared over 1 plus a squared lambda all squared. We subtract the value of the expected value of pi squared, which we also computed. That's right here. That's right here. So this was a squared lambda squared times sigma squared epsilon over 1 plus a squared lambda plus k minus yn squared. 1, 2. Okay, now our job, I mean, this is done, but we just need to clean it up a little bit. We just need to clean it up a teeny tiny bit, and there's a lambda here. It's not a very convincing lambda. Okay, redraw that parenthesis and put a little leg on this. Whatever, that's a lambda.
2 hours later.
Alright, I made a mistake. I was sitting there and I was like, why isn't this simplifying? Why isn't this simplifying? And I had to pause the video and I went back and I stared and I stared and I found the error. And I hope that you saw it as I was working, okay? If you did, that's awesome. Sorry, everything's messed up. Okay, what happened was in part 2, here, in part 2, when I took the square here, I forgot a square on the bottom here with this epsilon squared. So then I simplify, this is deterministic, this goes to 0, and there's a square here. That's squared. And then there's a square here for the expected pi. And then does that have ramifications for the expected y minus k? I don't think so. No, because yeah, there's no expected pi in here. We already simplified that away. Yeah, this is all good. So the difference is just when we have the expected pi squared, it's going to be right here. We have a squared, lambda squared. In fact, let's delete a bunch of this. Sorry, you might not even, maybe I have to edit this video, which sucks, but you might not even see me do any of this computation because I'll just cut it all out. Let me clear away this and clear away all of this. Okay, so here we have a square underneath. This was where the error was. Whoops. Pen mode. This is squared. Okay, and now it's nice because we have a square and a square. So I can factor out lambda minus lambda over 2 from both parts. Minus lambda over 2 yn minus k squared, there's a new parenthesis here, minus k squared, plus sigma epsilon squared, 1 plus a squared lambda squared, minus, I'm going to factor through a squared lambda. One lambda went out to the front when I factored that out. So I get a squared lambda over 1 plus a squared lambda squared sigma epsilon squared. And this is plus as well. I apologize because I factored out the minus sign. So this is plus and this is plus. Plus a squared lambda k minus yn squared. I see a k minus yn squared here, a k minus yn squared here. I can combine these, and I can also combine the epsilons. So I get minus lambda over 2. I'll use a square bracket for the big outside one. yn minus k squared. Let's write the coefficient first, I'm sorry. So bracket. It's going to be 1 plus a squared lambda yn minus k squared plus factoring out the sigma epsilon. So you get 1 plus a squared lambda. They have the same denominator, so I can just add them together directly. 1 plus a squared lambda squared sigma epsilon squared. Hunky-dory. And then you see there's a cancellation here. And I'll have 1 over a squared lambda here, and I'll have a squared, and then we can just get rid of that by multiplying everything by a squared lambda. 1 plus a squared lambda. Maybe. Yeah, I can divide and multiply, right? Just to get sigma by itself. So I could write this as minus lambda over 2 times. I mean, I guess let's just not do anything clever. Let's just leave it. This is what we get. 1 plus a squared lambda yn minus k squared plus sigma squared epsilon over 1 plus a squared lambda. There you go. Boom. Done. Draw a happy box. Whoops. So, oh, good gravy. That's long. I hope though that it's helpful to go through all this algebra and to see that when you have a really big problem, you split it into pieces. So what's interesting about this is that the welfare of the economy is influenced by the variance of the shocks. And if you think about it, that makes sense because the central bank is using the inflation rate to smooth output, right? It always wants output to be K. And when it's above K, then it will increase inflation. When it's below K, it will decrease inflation. We know from the the linear case that whenever the central bank chooses a non-zero inflation target, then there is social loss, right? So the higher the variance of the shocks, every time there's a shock, the central bank is off of its target, so it has to create inflation or deflation in order to bring it back to K. So the more shocks, then the more it has to use inflation and the larger the social loss. So that makes sense. And then also we see this yn minus k, which we already reasoned about, and we said that when the central bank chooses a target k that's very far away from the natural rate of growth, then it has to use the instrument, inflation, to get to k. So the bigger that difference, then the more social loss there is. And then it's all scaled by 1 plus a squared lambda, which is a combination of these two sensitivity parameters that we're determining the social loss in the linear case. So everything makes economic sense intuitively, I hope. It's a big grind to get there. But once you get there, you should be able to try to reason about your answer. And if it economically makes sense, then that's a really good thing. That's a good check. If you were to stop, if you were to stop here, I wouldn't blame you. But, it's harder, if we're just talking about like a test, right? If you stop here, did you get the right answer? I made this mistake. I knew that the answer was like this already. I had done it previously. And I also looked in the Wald book. So I had that advantage. And I knew I was missing this square. So I was like, wow, something's wrong. If you don't know something's wrong and you have like a big equation like this, these models that we study in class shouldn't end up with some huge long thing like this. This is pretty long, but it's not like huge long. This is like 2 pieces and there's still plus, plus, minus, plus. I think at most you should expect like 2 parts, like one addition inside of a bracket. So that should be a sign that there's still more simplification to go. Let's just double check the question really quick to make sure that we answered it. We can also reflect on everything that we did. Comment on the appearance of sigma epsilon, we did that. And then I guess in the next part we'll go back and look at part E. I don't think it's too much computation, but I already did so much. This video is so long. I'll see you there.